full disclosure, we are live and recording at this point in time. So, on page 153, if you have a book, there it is. There is an example problem right in the middle of the page. And yes, I realize that because it's an example problem, they do the problem for you right underneath it, but let's go through and see how it works and how they got all the numbers that they got. So it says, skiing downhill. A 62-kilogram person on skis is going down a hill sloped at 37 degrees. The coefficient of kinetic friction between the skis and the snow is 0.15. How fast is the skier going 5 seconds after starting from rest? So, first things first, right? What are we looking for here? Let's start with that. We're looking for velocity. Which velocity, more specifically? If it says after starting from rest, or 5 seconds after starting from rest, which velocity are we looking for? We're looking for final velocity. That is our unknown in this problem. Things we do know. What are some things they gave us to work with in the problem? Okay, they gave us the mass of the skier, 62 kilograms. Okay, they gave us that the angle is sloped at 37 degrees. They gave us the coefficient of kinetic friction as 0.15. And then spring, they also gave us what?
The time.
They also gave us the time over which this guy is rolling down the hill or skiing down the hill. Then there's one more thing that probably is going to be useful to us. What does from rest tell us?
The initial velocity.
Okay, just the initial velocity, right? Equals 0. Looking at this problem, the fact that we're looking for final velocity, they gave us like a time and an initial velocity. What does it look like we're probably going to have to do here to get to our final answer? Probably do a kinematic equation. Okay? However, if we look at kinematic equations, theta doesn't show up in kinematic equation, right? Mass doesn't show up in kinematic equation. Coefficient of kinetic friction doesn't show up in kinematic equation. So that only leaves us with time and initial velocity that we actually know. But how many pieces of information do we have to know?
3.
We gotta know 3. So that leaves us, we gotta find either what or what in order to solve this kinematic equation. Acceleration or the displacement. Alright, we good with information so far? Next, here's the picture. It's not a real great picture, but it's the one that from your book didn't really show up very well. Alright, let's talk about forces, because that's what the inclined plane problems are all about. So let's talk about forces. First force that we can put on our drawing. Gravity. And we know how to calculate gravity, right? Why don't you do that? So what did we find out for our force of gravity? 608.2. Okay, so 608.2 newtons. Now, in this situation, 2 other forces that are acting on the skier. Right? Okay. You got normal force, but like we talked about over the past couple of days, our normal force has to be perpendicular to the surface that causes it, right? So it's going to look something like that. Okay. So there's our normal force. And then one more force that's acting on this skier as it slides down the hill. There's frictional force that's going to act opposite of the motion. It's going to look something like that. Good so far? All right. How are we going to go about solving this problem? Any ideas?
We have to break into components.
Okay, we've got to break something into components, right? And do we have to go through the whole rigmarole of the axes and everything like that, or are we at the point where we know what we have to do? We got it? Okay. All right. So here, let me just do this real quick. So x-axis, y-axis, group them together, and then we'll make them dotted. There they are. Okay, we'll bring it over, we'll put it here, we'll rotate it 37 degrees, and there we go. Okay, so on the inclined plane, doing that, changing the axes, rotating the axes so that the x-axis is parallel to the ramp, the y-axis is perpendicular to the ramp, that results in our gravitational force not being on the x or y-axis, so we have to break it up into components. And we said that that gravitational force has a y component, right? And it has an x component, just like that. Make this a little bit that. Because this is the vertical component on the y-axis, and because this is the horizontal component along the x-axis, what do we know about the angle between those two?
37.
Nope.
Or that's 90.
This is going to be 90.
Yeah.
Okay. And then we also have gone through the process of, with this angle being the angle between the ramp and the ground being 37 degrees, that angle also has to be 37 degrees. So now, in this triangle, we have a way to figure out both the x component and the y component, or the component that is perpendicular to the ramp, and the component that is parallel to the ramp, or the hill in this case. So why don't you go ahead, go through, figure those out now, and move on from there. Just to reiterate, right, we said that when we're doing this triangle with the gravitational force, right, the force of gravity, the solid green line, always has to be the hypotenuse of this triangle. So make sure you're making your triangle correctly. All right. What did we get? Parallel component? 366. Perpendicular component? 485.7. All right, good there? Okay. What we've done, in essence, is taken this, kind of getting rid of this solid green, and replaced it with these two dotted greens, right? That's what component vectors are kind of like. Let's take a look first at the y-axis. Which way is the movement going in this problem? It's going down the hill, which just so happens to be along which axis? X-axis, right? Anything changing on the y-axis? No. There is equilibrium on the y-axis. Meaning, if we know the perpendicular component of gravity, right, what else do we know? Okay. The normal force in this case has to be the same because there is no change along the y-axis, and there's only two forces on the y-axis. Yesterday's example problem that I posted the video for, problem set number 7, that's not the case. Take a look at it. Now, what's happening on the x-axis, though? What does it say in the problem was going to happen here? So again, it's going to slide down, and if it started at rest and it's asking us for its speed after 5 seconds, Lori, what's going to have to happen while it's sliding down? Okay. Accelerating. So what can you tell me about this and this? They can't be the same, right? If they were, would anything happen? There would be no change. That's equilibrium, and that's not the case in this problem. Here, here. Do we know what red is? No. What information did they give us to work with for the problem? They gave us the coefficient of kinetic friction. If you think back, we know that the coefficient of kinetic friction looks like this. That's our definition of the coefficient of kinetic friction, right? The force of kinetic friction over the normal force. Do we have enough information now to calculate what the kinetic friction force is going to be? We do. We know the coefficient, it was given to us in the problem, right? We know we know the normal force because we figured out that the y-axis has to have equilibrium. So we know 2 out of the 3 things in this problem. We can figure out what the frictional force should be. And when you do that, what does it turn out to be? 72.9. 72.9? Okay. All right. What does that do for us? Thinking back to our original set of information, we said that we were probably going to have to figure out one of 2 things, right? What did we say was the 2 things that we could possibly figure out? Either the acceleration or the displacement. Do we have enough information in this picture to figure out one of those 2? You can do acceleration. These were the 2 conditions that we had for equilibrium, right? Okay. We've already established that on the y-axis, we're still in equilibrium. But are we in equilibrium on the x-axis? No. If we're not in equilibrium, Laura, you said that means what's happening? That there's what? There's acceleration. If we have acceleration, we know how to calculate the acceleration. If we look at the net force on the x-axis, that has to be equal to the mass times the acceleration on the x-axis, right? That's just Newton's second law. Newton's second law still holds true here, but it's only applying to which axis in this problem? Just the x-axis. Do we know the net force on the x-axis? Like, how many forces are there on the x-axis in this picture? Force of kinetic friction, and then the parallel component of gravity, right? And we know both of them. Like, because of the way they are in the picture, what are we going to do with the 2 of them? Which way are they pointing? Right, so what are we going to do with them? Subtract them, right? And we know the mass of the skier. Yeah. So in this equation here, that's not what I want to do. In this equation, we have enough information to calculate the net force on the x-axis. We know the mass, so we can use that to calculate the acceleration on the x-axis. Okay? Go ahead and start working on that. I'll put it up here.
Are you going to be...
Now, in this case here, right, we're only worried about the acceleration on the x-axis, right? Just these 2, just the red and just this one, because those are the only 2 on the x-axis, right? Are you good? Yeah. Okay. And I apologize because I'm going to make them green and red. Sorry.
Are sig digs going to even matter?
Let's not worry about sig digs at this point in time. I'm just not really worried about sig digs right now.
4.73.
And for the acceleration, we should end up with 4.73 meters per second. Is that the end of the problem, though? No. What did we originally want to know? No.
We need like the math.
Plus a negative, right?
So it's the negative is bigger than the positive.
366 and 72.
Oh, that's not.
There's
that's
nothing
not-
like
that's
that.
not-
No, it's 72.9.
Yes, I couldn't see the
So,
it's fine.
gotcha.
Thank you. That's
No problem. All right, so now we have an acceleration value. if we bring that back over here, right, we calculated that the acceleration along the x-axis is equal to 4.73 meters per second squared. Now, we know the initial velocity, we know the time, we know the acceleration. We can figure out what the final velocity is going to be. Yes. That's why we have to build up to it. That's why we want to start on this route. So that was just give it to you in the problem. How's that? Problems there?
It was intense.
But that's why I recorded it today, so you can go back and look at it and go, okay. Now, if you flip over to page 154, on page 154, number 7 in the practice problems section is very, very similar to this problem. You're changing the angle of the hill, and it only asks you to calculate the magnitude of the acceleration. So you can stop after that last step. Not quite as expensive, but very similar to what we just did. Okay? So, why don't you go ahead, start working through this problem. You got like 15 minutes left. That's enough. I will work it up on the board here and have it. I have to stop the recording now because that's finish saving before the end of the period. But I'll put it up here and I'll post the answer. I'll show you how I did it online. Okay.
To be continued.
Yes. Oh, I should do this actually before I finish the recording. So on page 154, number 7, very similar to that problem. Okay. Also, from the calendar, at the end of the chapter, page 171, number 36, number 37, and number 38. Very similar to the problem that we just did in class, okay, where we have motion along an inclined plane. It's not a constant velocity, it's speeding up motion. So we look at the difference between usually the parallel component of gravity and the frictional force, and that will give us the acceleration, and we can go from there. Okay? But first, start with page 154, number 7. So let's work on that so you can get that done before the end of the period. Okay?
There, some of the problems